Question 6a, part 1. State what is means by partition coefficient, KPC. Okay, this one is very straightforward. It's a ratio of the concentration of a solute in two immiscible solvent at equilibrium. The answer in the marking scheme a bit simple. This is a complete definition about the KPC. So if you want to know more about the KPC, the expression, so let's use this example. So KPC is equal to the concentration of the solute. In this question, the solute is X, and this solute will dissolve in one solvent. In this question is the CS2, and the solute also can dissolve in water, which is another solvent. And these two solvent is immiscible, so means it will form two layers later. It will be a partitions form between these two solvent. Okay, so this we call partition coefficient. Okay, so it's about the concentration of the solute in the two immiscible solvent. Okay, part 2. This is about the calculation. We have the compound X, and this compound X can distribute or can dissolve in the two solvent, carbon disulfide, CS2, and water. And the KPC given is 10.5. So 1.85 gram of X, the solute, is dissolved in water and make up to 100 cm cube. After that, 40 cm cube of this solution is shaken with 25 cm cube of CS2. So from here you need to do calculation which to get the mass of the solute in 40 cm cube. Okay, so let's say this is the one that started. 1.85 gram of X is dissolved in 100 cm cube and is in the VF. And after that, only 40 cm cube was taken, and you need to get the mass of the 40 cm cube in the aqueous solutions for the extraction. Okay, so very easy. You need to use a ratio, the smaller ratio, because it's just 40 cm cube from 100, so it's actually 40 over 100 times the total mass that added. So the mass of X in this aqueous solution is 0.74 gram. Okay, after that you can use this gram for calculation. Form the KPC expression if you can. So it's equal to the concentration of the solute in the CS2 over the concentration of the solute in water. Okay, because it's already mentioned is between the CS2 and water, so the expression is like this. Okay, now 10.5 is equal to the concentration. Now it can be expressed in the gram per cm cube. So let's say Y gram of the X now is get extracted by the CS2 and is over 25 cm cube. Okay, this is the concentration of the X in the carbon disulfide. Okay, after that, this one is divided by the concentration of the X in water. So because we know that some of the mass in the aqueous solution already get extracted and is from the total mass of 0.74. So therefore is 0.74 minus Y and over 40 cm cube. This is the concentration of the X in the water after the extraction. Okay, then you need to rearrange and you get the Y is 0.642 gram. Means the mass that being extracted now is 0.642 gram. Part B. The compound C6H6 has many structural isomers. Four suggested structure of this C6H6 are shown in this figure 6.1. And so they are Kekulé benzene, they were benzene, Landenberg benzene, and delocalized benzene, these four. And now this question is using this figure 6.1, complete the table 6.1 to predict the numbers of carbon atom that has sp2 and sp3 hybridization in this three structure, the first three structure. So for the first one, we know that this calculate benzene. So all the carbon is actually sp2 carbon because it's a six carbon here, and they all have the double bond. So therefore we know that all these carbon is the sp2 carbon. Okay, so for this the second isomer, so we know that this is the sp3 carbon because it has 4 bonding. So 1, 2, 3, another one is with hydrogen. So this is sp3 carbon and this is sp3 carbon. So therefore there are 2 sp3 carbon there, and these 2 carbon and these 2 carbon, they have double bond. So they are sp2 carbon. Means in this isomer, it has 4 carbon with sp2 hybridization and 2 carbon with sp3 hybridization. Okay, so again, the first isomer, calculate benzene, it has all 6 sp2 hybridized carbon. For the second isomer, it has 4 sp2, 1, 2, 3, 4, and 2 sp3, right here. And the last one, because there is no double bond, so all sp3 carbon, so all these carbon actually has 2 hydrogens bonded with it. Okay, all the carbon has 2 hydrogen. So therefore, all they are sp3 hybridized carbon. So you just put 6 here. Okay, for part C, describe the shape of the delocalized benzene. Of course, delocalized benzene, it should be a circle in the middle. Okay, but it's actually better to use the just now the calculate structure. It is clearer, so you can get the type of bond and the bond angles easier. Okay, so include the geometry of each carbon and the CCH bond angle and the types of bond between carbon and carbon and the carbon and hydrogen. So first, we need to know the geometry of the carbon. So in the benzene, the geometry of each carbon is trigonal planar. Why? Because all these carbon, as I told you just now, they are sp2 carbon. sp2 carbon means the carbon has 3 bonding pairs, means 3 electron clouds, and they are bonding pairs, and therefore it has the this trigonal planar geometry. So each of these carbon, they're having the trigonal planar geometry. Okay, this one, first one. And for the CCH bond, okay, CCH, let's look at this. Okay, CCH, let's choose these 3. CCH, so is because the carbon is trigonal planar, therefore the bond angle here, it must be 120. Right, 120. And between the carbon atom, what is a type of bonds? So between the carbon-carbon, we know that it's double bond. You can see here. So double bond means there will be 1 sigma bond and 1 pi bond in there. Right. So you just need to put between the carbon's atom, it has the sigma bond and the pi bonds. Between the carbon and hydrogen, let's say here, so only sigma bonds. So this is type of bonds between the atoms. Part D. Suggest why Ziwa benzene and Landerberg benzene are unstable isomers of the C6H6. Okay, so this question is quite rare in the past year. Okay, however, let's see how the explanation to be. As these 2 structural isomers have the sp3 carbon with tetrahedral geometry in the ring, it will cause the ring strain, means more repulsion. Okay, so let's look at the structure and compare. So for this delocalized benzene, so we know that all these carbons, they are sp2 carbon, and there are only 3 electron clouds surrounding the carbon, and the repulsions between the electron cloud is relatively lesser as compared to these 2 isomers, right? So because only 3 electron clouds. For this Ziwa benzene, we know that there are 2 carbons here. They are sp3. So this one is sp3, and this one sp3 as well. And the rest, they are sp2. Okay, because this sp3 carbon, as you can see, there are 4 electron pair there, and all these electron pair, they have repulsion. So means it will cause the ring relatively unstable compared to this delocalized benzene. Same as this landable benzene. As you can see here, all these carbons they are sp3 carbons, and tetrahedral geometry, of course, and each carbon, they have 4 electrons pair, and of course the repulsion is always there. Means it's relatively unstable for this 2 ring structure, or these 2 isomers. That's how the expression to be. Okay, now let's see the part E. Complete table 6.2 to predict numbers of peaks in the Proton NMR for the Ziwa benzene, landable benzene, and delocalized benzene. Okay, let's start with this Ziwa benzene. Okay, let's check. For this one, there are 4 protons having the same chemical environment. Okay, this one, this, and this. They have the same chemical environment, means they are equivalents, and they will produce only 1 peak or 1 signal. And the other 2 protons here, they have the same chemical environment, so they will produce another peak. Means total is going to produce, okay, this one is 1 signal, and another one, this one, will produce another peak, right? So means for the Ziwa benzene, it will be 2 proton peaks there, because there are 2 different protons chemical environment. For the landable benzene, as you can see here, right, all these protons, they are kind of like equivalents, you see, right? So means they're having the same chemical environment, and they will produce 1 peak only. Okay, so for this delocalized benzene, it's easier to see. Okay, all these 6 protons in this delocalized benzene, they are also having the same chemical environment, so it will produce 1 peak. Okay, for these protons in the benzene. So this is the answer. Okay, part F. The reaction of the phenylethanone, right? So this one is ketone with 1,4-dibromobutane in the presence of the FeBr3. So this is a reaction is given, and the mechanism of this reaction is similar to that alkylation of benzene. So means it's electrophilic substitution. Now, for the first part, construct an equation for the formation of electrophile. This one, actually there is a small mechanism, but you no need to give the mechanism, you just need to give this equation. It's actually one of the bromine will donate its lone pair to the catalyst, this FeBr3, and eventually it will form this intermediate. So the CBr bond will break, and the 2 electrons will move to the bromine, and eventually it will form this FeBr4 negative. So it's electron rich. The electron deficient, of course, is the one that this part. Okay, the bromine with the 4CH2 here, so it will form this carbocation. Okay, so this is equation, means you just need to put one bromine here with the FeBr3, and you put the charge there, FeBr4 negative, and this carbocation. Part 2. Complete the mechanism in the figure 6.3 for the reactions of these ketones and the carbocation. Okay, it's very easy. This mechanism, it been asked many times. So first, you need to draw one arrow from the benzene ring of the ketone. So point to the carbocation. Okay, so this one basically will give you 1 mark. And after that, it will form this intermediate. So for this intermediate, you need to draw a partial charge here. Means you need to draw a curve and put a positive charge in there. And this one is to show that there is a partial charge formations for this intermediate. And of course, you need to show the CH bond here. And of course, the bond, the new CC bonds formed here, okay, with the carbocation just now. And another one, you need to draw one arrow from the CH bond, point back to into the ring, to show that this pair of electrons will move into the ring and restore the benzene ring. Eventually, it will form this compound. Of course, these hydrogens will remove as the proton, right? So this is a substitution, electrophilic substitution. Okay, part 3. The reaction shown in the figure 6.2 forms small amount of 2 byproducts, okay, Y and Z. So this one you need to compare the molecular formula, see what is going to form. Okay, so let's start with the Y. Okay, how to get this Y? This is the answers in the marking scheme. First, you need to know because there might be a side reactions, Okay, let's say after the formations of this product as shown here, okay, just now these products, okay, after it's formed this, then it might further react, So means this catalyst will react with the products, and because here got the bromine, the CBr bond. So if you react with the catalyst and it's formed the carbocation, and the carbocation here will react with another ketone. So this is the first starting compound, and it will undergo another electrophilic substitution. So means it will form something like this, right? So means again the electrons from the benzene now is donates to this carbocation and form new bonding, and eventually electrophilic substitution, and it will form this compound. That's how you get the C20H22O2. Because from this the molecular formula, we know that the size increase, because initially is from for these products, for the products in the previous part, is just C12H15OPr, because now it's increased by 8 carbons, right? So we know that it must be another molecules, another ketones that add in, because it's 1, 2, 3, 4, 5, 6, 7, 8. So because the ketone that used initially total 8 carbon, so we kind of can predict is actually the reactions of the products with the starting material and form a larger molecules. So that's why we get this. This is how you deduce the reactions and the products, right? So therefore you can get this Y. Okay, so I redraw it. So this is the same as the mark scheme. The structure is similar to what I showed you just now. And for the Z here, so it's C12H14O. Then we need to compare. The product is the product is this C12H15O. So we know that if we compare with this one again, C12H14O means their different is HBr, means the products here, has extra HBr compared to the Z. So we kind of know that it's going to remove the HBr. Remove HBr, because once the HBr removed, this one become 14, this one gone. So it will form the molecular formula of the Z, C12H14NO. So we kind of know that now a similar reactions will happen the first stage. The catalyst will still react with the products, and it's formed the similar carbocation. But now this carbocation is not going to react with another ketone. It's going to react with its own benzene, something like this. So the benzene, the electrons from benzene now is is donate out and form bonding with this carbocation. So eventually it will form this ring. You see the numbering, 1, 2, 3, 4. So this carbon will form a bonding with this carbon. So eventually form this ring structure. So this is the Z. So this is how you deduce the structure of the products, right? This is quite a long question. So this one already done. Many thanks and all the best for your coming exam. Bye bye.